Okay, in this section, we're going to relate energy to power. So let's define power. Power is the rate of doing work, or the rate at which work is being done, the rate at which energy is being consumed or transferred, and the equation for that is P is equal to, so power is equal to work divided by time, which makes sense because you're looking at a rate. So rate usually involves a time component, or power is equal to energy divided by time. And as we've discovered earlier, energy and work are interchangeable. Okay, so now let's talk about dimensions. So we know that power is equal to work or energy divided by time. So work or energy is measured in joules, as we know, and time is second. So power is joules per second, and the unit for that is a watt. So symbol is W, and that represents watts. Because we're usually dealing with larger units when we're dealing with power, it's often convenient to express energy or power in terms of these larger units. So let's just review some of these. So 1,000 joules is equal to 1 kilojoule. And in terms of power, 1 kilojoule per second is equal to 1 kilowatt. Now let's look at 1,000,000 joules, and we know 1,000,000 is mega, so it'd be 1 megajoule. And in terms of power, 1 megajoule per second is equal to 1 megawatt. Okay, 1 billion joules is 1 gigajoule, and in terms of power, 1 gigajoule per second is equal to 1 gigawatt. And now you can understand the movie Back to the Future a little bit more. Now let's do an example. An elevator and its occupants have a mass of 1,300 kilograms. The elevator motor lifts the elevator to the 12th floor, a distance of 40 meters in 74.8 seconds. What is the average power output of the elevator motor? So first thing, let's write down our givens. Okay, so in this case, we want to calculate power. So we know power is equal to energy divided by time. In this case, you're lifting the elevator to a height, so you know that you're going to have some gravitational potential energy. So your energy here is going to be equal to your gravitational potential energy, and you know your gravitational potential energy is equal to mass times gravity times height over time. So if we sub in our values, that's our mass. Our gravity is always 9.8 meters per second squared, and your height is 40 meters, and your delta T is your time that's elapsed, so that's 74.8 seconds. And that gives us a total of 6,812.83 watts. And that equals 6.81 kilowatts. So remember, kilowatt is 1,000 watts, and we have 3 decimal places here, so that's 1,000. You're just dividing by 1,000, so 6.81 kilowatts. Okay, on to another example. If the power of a motor is 5.6 kilowatts, how much work can the motor do in 20 minutes? So now we're looking for work. So first thing, again, let's write down our givens. Okay, so in this case, 5.6 kilowatts, we're just converting into watts, right? You want to work with your base units. So in this case, it's watts in seconds. So that's just 5,600 watts. And 20 minutes, 20 times 60 is going to give you 1,200 seconds. So we're looking for work this time. So obviously we're going to use work instead of energy. So power is equal to work divided by delta T. And let's solve for work. So cross multiplying, we know that work is going to be power times delta T. And now we can just sub in our values. So your power, remember to work in watts and seconds. So this gives us 6,720,000 joules, which can be shortened and simplified to 6.72 megajoules. And so the motor does 6.72 megajoules of work. When we're dealing with power efficiency, we want all of our input energy to go towards our output. So we know that when energy is transformed from one form to another, that some of the energy is lost to the surroundings. For example, an incandescent light bulb uses electrical energy to produce light, but how efficient is this process? Does 100% of the electrical energy get transformed into light or radiant energy? In fact, most of the energy is transformed into heat or thermal energy. So it's 95% thermal and 5% radiant. So how efficient is this process? We can say that the light bulb is 5% efficient. So mathematically, this can be described as E, which in this case is going to be efficiency, is the change of energy that's coming out, so your output energy, over change of energy going in. So it's just that ratio. Or alternatively, we can say that efficiency is also the amount of power coming out and over the power going in. Therefore, if 100 joules of energy is input into the light bulb, how much is transformed into light or radiant energy, and how much is transformed into heat and thermal energy, which is waste? So using our efficiency equation, we know that the efficiency for light is 5%, so that's going to be 0.05. And you know that your input value is 100 joules of energy. So we want to find out what our output is. This is going to be 100 joules. And your output energy is going to be cross multiply. You get 0.05 times 100 joules. And that gives you 5 joules. Let's do it for heat. So your efficiency for heat would be 0.95, so 95%. This is assuming that you want heat, and that's an efficient outcome. And your input energy, again, is 100 joules. It's kind of predictable what this is going to come out as. This is just going to be 0.95 times 100 joules, and it's going to be 95 joules. We've seen appliances in our homes or advertisements saying that appliances use a certain amount of energy in units of kilowatt hours. So what do these units mean? Kilowatt hours are usually written as kWh. So kilowatt hours, you've probably seen that symbol. It turns out that these units use the same equations and principles of measuring energy and power as we've seen above. However, in terms of our everyday lives, it's often more convenient to use kilowatt hours instead of joules or watts. Let's do a little comparison between our SI units, which is what scientists like to use, and our household kilowatt hour units. Well, we know that power is equal to energy divided by time. And so energy would be power times delta T. In this case, if we're looking at kilowatt hours, your power is going to be kilowatt, which is 1,000 watts. And in an hour, which is usually measured in seconds, is 3,600 seconds. And so that gives us 3.6 times 10 to the power of 6 joules of energy. Let's take that same rearranged equation. So energy is equal to power times time. And in terms of our units, we know that power is going to be measured in kilowatts for the household type of kilowatt hours units, and time is going to be measured in hours. So in this situation, your energy is going to be 1 kilowatt hour. So we've done the same thing on both sides. We can conclude that 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. So important note, this means that if we're given energy in terms of kilowatt hours, we must ensure that our time is in hours in order to get an answer for our power in kilowatts. An example of this, an old 17 cubic foot frost-free refrigerator uses 450 watts when it is running. Assume that the refrigerator runs 5 hours each day. Part A, we want to determine the amount of energy consumed in a day in joules and kilowatt hours. So let's write down our givens. Okay, so I've converted these so we have both options. So we have watts and kilowatts and hours and seconds. Now we're going to look at joules. So we're going to calculate the energy. So we know power is equal to energy over time. So energy is going to be equal to power times time. And plug in your values. You know to use watts for this, so 450 watts, and seconds. And that gives you 8.1 times 10 to the 6th joules. Okay, now let's do the same calculation, but in terms of kilowatt hours. So I'm just going to use that rearranged equation that we came up with. Energy is equal to power times time. And your power, since we want it in kilowatt joules, you want it in kilowatts. So 0.45 kilowatts, and hours for time, so 5. And you get 2.25 kilowatt hours. And these values are equal, it's just expressed differently. Part B says determine the annual energy consumption in kilowatt hours. So now we want to know kilowatt hours per year. So we're just going to have to convert our value. Easiest thing would be to convert the value that you used for kilowatt hours. So we know we got 2.25 kilowatt hours, and that was per day. So to convert that to year, we know we want the top to cancel out, so we have 1 year on the bottom. And how many days is that? 365 days. I know it's 365.25. I'm just going to use 365. And that gives you 821.25 kilowatt hours per year. Okay, so just to summarize, perhaps add these equations to your ever-growing formula sheet. Your power is equal to energy divided by time, or similarly, work over time. 1 kilowatt hour is equal to 3.6 times 10 to the power of 6 joules. We calculated that earlier. And this is efficiency, which is equal to the ratio between the output power to the input power, or the output energy to the input energy. That's it.